All right, so we're on to lecture 22. And in this lecture, we're going to kind of continue on with what we talked about last time, which is kind of understanding how molecules are put together. So that kind of began with understanding Lewis structures. Now, beyond Lewis structures, we're going to look at two more ideas. We're going to look at, well, if we could see molecules, what would they look like? What are their shapes? And then there's one important property that we haven't gotten to yet that kind of has a lot to do with the way molecules behave. And that is really polar and non-polar molecules. What's the difference? All right, so that'll be kind of the goals for this lecture. And with that, let's go ahead and get started looking at shapes of molecules. Okay, so before we kind of get into looking at how we determine the shape of a molecule, let's just spend a minute talking about why do we care about the shape of a molecule. And so this is sort of a kind of a big molecule. It's called dopamine. So it's a molecule that's active in your brain. It's kind of like a stimulant. And if you look at its structure, you can see, oh, well, some of these things we've already talked about, right? Like it's got some single bonds and it's got some double bonds and so on. So yeah, a little bigger than what you've seen so far. But if you look at its shape, the way it's put together, it turns out that has a lot in common with other molecules which people might take, which are also stimulants. So dopamine is sort of like the stimulant that's naturally in your body, but it has a similar shape to, well, let's put up a few more, like ephedrine, which is sometimes found in cold medicine and so on. And then, well, one you're not supposed to be taking, methamphetamine, right, meth. So if you look at all of them, they have similar similar shapes, and they actually lead to similar responses in your body, right? So you need a stimulant to kind of keep you awake and active, and if there's some danger to warn you about it, kind of that's what dopamine's job is. And then you can take some maybe when you're not feeling so good to make you feel a little better, like ephedrine. And then, yeah, sometimes people get addicted to that feeling and they take ones they're not supposed to. Again, the reason why they all do similar things in your body is that they have a similar shape. So understand this shape. The shape of a molecule often goes along with the way that it's going to interact with things, including people. All right, so with that little introduction, let's talk about, well, how do we determine the shape of something? Now, I should tell you, we're not going to look at these big molecules too much. We're going to look at small molecules in this class, all right? So, so far, we've talked about Lewis structures. Now, Lewis structures don't really tell you the shape. What they tell you is the type of bonding. They tell you, are my atoms connected by single bonds? Or are they connected by double bonds? Or are my atoms connected by triple bonds? So it turns out, though, we need to know that to be able to understand the shape. But that's not enough information. You need to also look at one more idea. And that idea is called Vesper Theory. All right. So we're going to build on it. We're still going to look at Lewis structures, but we're going to add another layer to that idea. And that other layer is called Vesper Theory. So Vesper, that's an acronym. So let's talk about what it stands for. VSPR. All right. So V stands for valence. S stands for shell. E stands for electrons. So we're going to still focus in on the valence electrons, right? Those are the ones that are used to bond. And just like we saw before, they're going to be in pairs, maybe a lone pair or a shared pair. So that's what the P stands for, pair. And then kind of the heart of this theory is the R, really, repulsion theory. So repulsion, that means to be repulsed by someone. That means, ugh, stay away. And that's basically the idea behind this theory. The idea behind this theory is that electrons don't like each other. And they're going to try to spread out as much as possible around the middle atom. So they're going to do whatever it takes to get away from each other. Now, a way of saying that is they're repelled by each other. So we're going to go through some examples of, well, if electrons are trying to spread out, what does that mean as far as what shape will they take? All right. So there's about, let's see, I think 5 common shapes we're going to go over. There are more that exist in the world, but we're going to go over the 5 most common ones. And like we'll look at an example, and then we'll try to understand why is it making this shape. And it really all boils down to this idea. Electrons are trying to get away from each other. All right, so let's go through what shapes do most molecules come in. Okay, before we get to those shapes, those 5 common shapes, let me just mention one more fact. And that is there's really 2 ways we talk about the shapes. And this might be a little confusing at first, but hopefully eventually it'll make sense. One way we talk about the shape is called the electron domain geometry. So what is that? That's really the shape the electrons around the middle atom make. And then there's also another term that's called the molecular geometry, and that's the shape the atoms make. All right. So sometimes these shapes kind of go together and sometimes they don't. As we go through our examples, hopefully you'll kind of see the difference. All right. So one has to do with what are the electrons doing to get away? And then what does that make the atoms do to get away from each other? All right. So with that, let's look at our possible shapes that you need to be familiar with. All right, so our first possible shape, an example of it is carbon dioxide. Now, I should tell you, the first thing you're going to have to do to figure out the shape, you're going to have to draw out the Lewis structure. I already talked about that in the last lecture. I'm not going to go over drawing Lewis structures again. If it didn't make sense, you can rewatch that lecture, right? Or help me, ask me some questions or whatever, all right? So if you draw out the Lewis structure, this is what you'd come up with. This is the Lewis structure for carbon dioxide. Now, what I want to think about is, well, what's around the middle atom and what's going to happen to get those electrons away from each other that are around the middle atom. So to help you kind of see this, at least for the first 1 or 2 here, I'm gonna kind of imagine if I could see a molecule, what would happen. All right. So we'll let this big sphere here be like the carbon atom, and we'll let this these sticks be my electrons. Now, in this case, the carbon is double bonded to an oxygen, all right? So I might need to back up a little bit. There we go. Now that is like a carbon to 1 oxygen, but remember, it's actually got another oxygen. So let me add the other oxygen. And let's think about where would that other oxygen want to be if they're trying to spread out. Now, this is not the best they can do. If these atoms are trying to spread out, and these electrons really, these 4 are trying to spread away from these 4, this is not the furthest they can do. They can get further away from each other. This atom and these electrons can get further away if they end up on the opposite side. Now, if they kept going, they would get closer to each other, right? So the farthest away they can get is to be on the opposite side of the carbon atom. So that idea that these elements, these electrons, are going to spread out from each other, that's what Vesper theory is all about. Now, let me show you a picture of this. So because they're trying to spread out, what's going to happen is these 2 sets of electrons, that would be like this double bond here, is going to try to get away from this double bond, that would be like this double bond here, and they're going to get on opposite sides of the carbon atom. So when you have this shape, this is called being linear. All right, linear, this is the name of this shape. Now, it turns out the electrons are on opposite sides of the carbon atom, so the electron domain geometry is linear. The atoms, the oxygen atoms, are also on opposite sides of the carbon atom. So the molecular geometry is also called linear. Everybody's in a line. All right. Now, the other thing that might help you, just to kind of get a feel for this, if we think about how far apart are they around the middle atom, they're 180 degrees apart. They're on opposite sides from each other around that middle atom. All right, let's do some more examples. It'll probably make more sense when you see some more examples. All right, so let's move on to another possibility. Oh, by the way, I should tell you, this possibility is going to happen when you have 2 areas around the middle atom. If there's 2 areas around the middle atom, this is the best way for those 2 areas to get away from each other. So this area and this area will be on opposite sides. All right, let's move on to another example. So another example again, and I got to put up the Lewis structure just to kind of show you it. We're not going to go ahead and draw it, but I'm following all those rules you heard last time, right? Give everybody 8 electrons and use the right total. So this is an example of, this is what formaldehyde looks like. So formaldehyde, you might have heard of it. It's used in like as a preservative and like biology and stuff. So I want to think about, in this case, what's the best way for these areas to get away from each other? Now, one way to do that, really where you want to start, is just to count up how many areas contain electrons. In carbon dioxide, there was 2 areas around carbon with electrons. This time, though, there is 1 area, 2 areas, 3 areas. So if you have 3 areas and they're all trying to spread out, this is the way they spread out the best. They look like that. So the 3 areas, so the gray guys are my carbon. So there's like 1 area, 2 area, 3 areas. Those 3 areas with electrons are going to get away from each other, and they're going to form a triangle. So what do we call this shape? If the electrons make a triangle, the electron domain geometry, well, we have a term for this. It's called trigonal planar. Trigonal planar. Now, the atoms, what are the atoms doing? So the atoms are like those spheres. This guy, and this guy. The atoms are also making a triangle, right? They're also making a triangle. So the molecular geometry is also called trigonal planar. So you can notice that they're kind of doing the same thing. That won't be true in a minute. But for right now, they are. The bonds form a triangle. The atoms make a triangle. So when is this going to happen? When is something going to look like a triangle? Well, the way you're going to know it is if you look at the middle atom, which is carbon, and there's 3 areas around the middle atom with electrons. 1, 2, 3. So this and this and this, it's going to make a triangle. All right. So 2 areas, you're going to make a line. 3 areas, you're going to make a triangle. Well, what if there's 4 areas? Well, that's really the last cases. You could have 4 areas around the middle atom with electrons. What's that going to look like? Well, let's flip over. All right, so 4 areas, an example of that is CH4 is methane. And again, if I draw out the Lewis structure, this is what it would look like, right? Yeah, there's 4 areas. 1, 2, 3, 4. So I'm just counting how many things are around the carbon. There's 4 areas with electrons. And this is one that might be a little hard to predict because, we're used to dealing with flat things, right? Like your piece of paper maybe in front of you right now. Hope you're taking some notes, right? So, but the world isn't flat. The world is 3-dimensional. So if these 4 areas are trying to get away from each other and that it's a 3-dimensional, world they're living in, the best way they can get away from each other is they can form this shape. It looks kind of like a pyramid, or sometimes people will say like a jumping jack sort of thing, right? So they'll form a pyramid shape. So first off, let's just confirm. I think I mentioned, yeah, there's 4 areas in here. Let's double check. So let's look at the electrons. 1, 2, 3, 4. There's 4 areas with electrons. So those 4 areas are all getting away from each other. So this is called, the electron domain geometry is called tetrahedral. That's what we call this shape. It looks like a tetrahedron. Now, what about the atoms? If I focus in on the atoms, they are also at the corners of a tetrahedron. So the molecular geometry is also called tetrahedral. All right. So let's move on. Let's do another example. All right, another possibility. Another possibility is this is ammonia. Ammonia, you might use it to clean your floors and stuff. Now, if I ask you what shape is it going to make, well, first thing you do, you count up how many areas around the middle atom contain electrons. Now, this time again, there's actually 4. A lone pair counts as an area. 1, 2, 3, 4. All right. So a minute ago, we saw a molecule with 4 areas with electrons. CH4 had 4 areas. This guy also has 4 areas. It's got 3 bonds and a lone pair. So it also is going to look like a tetrahedron. So the electron domain geometry, there's 4 areas with electrons. This thing is going to make a tetrahedron. So seems the same, right? But there's one difference. At one of the corners, instead of being an atom like we saw a minute ago, at one of the corners there's a lone pair. So if we just look at what the atoms are doing, the atoms are making this shape. The molecular geometry, which is what we call the shape the atoms are making, is called trigonal pyramidal. Trigonal pyramidal. So the 4th corner of the pyramid is a lone pair. So that's why it has a different name. All right. So there would be like a lone pair up here. Well, you can see it in this diagram right over here, can't you? All right. So the atoms are making, kind of looks like a short pyramid, or I guess, or something. All right. One more possibility, and we're going to sum it up, and hopefully that'll help it make a little more sense. Okay. Last possibility, water. Water has, again, if we look at what's around the middle atom, there's 4 areas. Uh-oh, this sounds a little familiar. 1, 2, 3, 4. There's 4 areas with electrons. A bond, 2 bonds, and then 2 lone pairs. So altogether, those 4 areas are going to be at the corners of a pyramid again. Whenever there's 4 areas, it forms a pyramid shape. So the electron domain geometry, the shape the electrons are making, they are at the corners of a pyramid. I guess this would be, I should be circling this, shouldn't I? Those are the electrons. Okay, so it's still called tetrahedral. All right, the molecular geometry, that's the shape the atoms are making. Now, it's going to be different because only 2 of the corners are atoms. So if we look at what the atoms are doing, they're doing this. The atoms sort of make, kind of looks like a V almost. The atoms are sort of like in a V shape. So if we focus on the atoms, that's really what it would be, what the atoms will look like. The atoms are like in a bent line. So it's not linear. Those things are not in a straight line. So it's called being bent. That would be the molecular geometry. All right, so that's kind of a quick run view of all the options. Let's try to sum it up, okay? Let's try to sum it up. So to sum it up, let's look at a little chart where all these options are, and let's just see, like, is this sort of making sense? All right, let's do a little summary of what we've seen so far. Okay, so this goes over all the common shapes that you should be familiar with. All right, so what I'm going to ask you, what you're going to have to practice is, I might give you a molecule and I say, what's the shape of this thing? Linear, tetrahedral, whatever. So the way you're going to know is you're going to look at the middle atom and you're going to see how many areas around the middle atom contain electrons. So if there's a lone pair or a bond or a double bond, they all count as an area. So you got to hunt for the middle atom, and you got to see how many areas around the middle atom contain electrons. So for example, in carbon dioxide, there is 1, 2 areas around the carbon with electrons, a double bond and another double bond. If you see 2 areas and they're both bonds, like a double bond, that's a kind of bond, right? Then the shape is called linear and linear. The electrons are making a line, the atoms are making a line. If you count around the middle atom and you see 1, 2, 3 areas, that is a molecule that's going to look like a triangle. So 3 areas, it's called trigonal planar, trigonal planar. All right, now I'm going to skip over the next one for a sec. Now, what if you have 4 areas around the middle atom? If you have 4 areas, 1, 2, 3, 4 areas around the middle atom. Now, this time, there's actually more than one option. If there are 4 areas and they're all bonds, that's called tetrahedral, tetrahedral. The atoms make a tetrahedron. The electrons make a tetrahedron. Now, what if you look around the middle atom and you see 4 areas again? but one of the four is a lone pair. So, like in ammonia, do you see how there's 3 bonds? 1, 2, 3 bonds, and then a lone pair? In that case, 4 areas, 3 bonds, 1 lone pair, that's called tetrahedral trigonal pyramidal. And then the last one is you might have 4 areas, but 2 of the 4 are lone pairs. If you have 2 bonds and 2 lone pairs, that's called tetrahedral bent. Water was an example of that. All right, you notice there's one on this chart that I kind of skipped over earlier. It's not as common. You can have 3 areas, and 1 out of the 3 is a lone pair. That's called trigonal planar bent. You might see that. It's not as common though. All right, so those are all your possibilities. So you look at the middle atom, you see what's around it. That's going to tell you the shape. So with this chart, you should be able to figure out the shape of any, well, small molecule at least. All right. So we'll do a little practicing. Hopefully that'll help this make a little more sense. The key is find the middle atom, see what's around it, and then match it up to this table, basically. All right. So I feel like there's something else I was going to tell you on this page, but now, oh, I know what it is. Well, we'll do that when we get to the example. All right, let's move to the example. Okay, let's do a few examples of determining shape. All right, so first thing you're going to have to do to determine the shape, you got to draw out the Lewis structure. All right, so I'm going to do one that we figured out the Lewis structure of in the last lecture. So if you don't have the Lewis structure, you can't do this. All right, so job 1, we're going to draw the Lewis structure. So one that we did a little while ago in the last lecture, I suppose, was this guy, HCN. All right, so I'm not going to go through all the steps of doing it again. You know, gave everybody 8, used the right number of electrons. So what I want to talk about now is, if you know the Lewis structure, can you tell me the shape? So how do you figure out the shape? You look at the middle atom, which is carbon, in this case, and you see how many areas contain electrons around it. In this case, there is 1, 2 areas. So there's a single bond, and then there's a triple bond. That's 2 areas. So if you have 2 areas, you're going to be this top possibility. 2 areas, the electron geometry is linear, the molecular geometry is linear. This thing would look like this. The atoms would be in a straight line, just one right after another. So it's called linear. All right. All right, with that, there's one more on here. I'm going to let you think about it, okay? So this is the Lewis structure for this molecule, NH2. It's got a minus charge. All right, so you see the Lewis structure there. You might need to think about it. You're about to get a little pop-up question. What's the electron domain geometry? What's the molecular geometry? Look at what's around the middle atom. Match it up with the table. Okay. Oh, there's going to be one more. Okay, so hopefully you got that right. The electron domain geometry, the molecular geometry. Well, let's go over it just to make sure. The electron domain geometry is, well, around the middle atom, there are 1, 2, 3, 4 areas, because a single bond is an area and so is a lone pair. There's 4 areas. Now, of those 4, 2 are bonds and 2 are lone pairs. So I think we got this bottom possibility. It's going to look like this water molecule, actually. So 2 bonds, 2 lone pairs. Yeah, 2 bonds, that's this column. 2 lone pairs, that's this column. So it's tetrahedral. And then the molecular geometry is bent. It should look like that. All right. All right. Let's take this just a little bit further. Okay. So, like I said, this is how you figure out the shape of a small molecule. But the same thing is true when you have a bigger molecule. If you have a bigger molecules are really just combinations of these shapes. So let's look at a molecule that's a little bigger and see if we can figure out what shapes does it contain. All right, let me flip over and we'll get to that. All right, so this is a bigger molecule, right? Way bigger. But again, the molecule is really just going to be a bunch of these shapes put together. That would be its overall shape. So depending on where you look, you might get different answers. So in this question, it says, what's the molecular geometry around atom number 4? So they've numbered the 4th atom right here, this fella right here, this carbon, I suppose. And they want me to tell them, well, what's the shape around that thing? Now, if you look around that carbon, what do you see? I see 1, 2, 3 areas with electrons. So if there's 3 areas of electrons, 3 areas with electrons around that carbon, 2 single bonds and I guess a double bond. I don't have that chart up, but you might remember 3 areas was called trigonal planar. All right. So depending on where you look, you get different shapes. So I'm telling you, look at carbon 4. I numbered them. That's the shape at carbon 4. All right, with that, let's see if you can do one like this. All right, let's try one like this. So big molecule, you can still determine the shape by looking at one area at a time. All right, so this one, oh, I guess this is the same molecule, isn't it? What's the shape this time at carbon 1? At this guy right here, this carbon right here. Oh, there we go. So this carbon. So see what's around it, match it up. I want to know the electron geometry around that guy. What's the electron geometry? What shape are the electrons making? All right, it should be, let's see, around that carbon, carbon 1, if I count them up, 1, 2, 3, 4 areas. They're all bonds, so that's called tetrahedral. All right, with that, that's it for shapes. We'll practice this a little bit in Zoom time. Part B, we got to move on to something else. All right, if you got questions, you can always email me or call me or whatever. All right.